All right, welcome back. So I'd like to start by reviewing some of the material that we covered just before spring break. Before we left, we were talking about weak acids and weak bases. We mentioned that the pH of a solution can be calculated by taking the negative log base 10 of the concentration of H plus cations in solution, the pOH of a solution from the negative log of the hydroxide ion concentration, and that based upon the Kw, the autoionization equilibrium constant for water, we derived that the pH plus pOH for a solution must equal 14 at 25 degrees Celsius. Today what we're going to do to start is calculate from the pH of a solution the concentration of H plus cations in the solution and the concentration of hydroxide ions in that same solution. To begin, let's take advantage of the first equation that we've got for pH. We know that if pH is equal to the negative log base 10 of hydrogen ion concentration and that the pH is equal to 5.5, then 5.5 is equal to the negative log base 10 of hydrogen ion concentration. How do we undo this log? Well, the first thing we've got to do is move this negative sign over to the other side. Negative 5.5 equals the log base 10 of hydrogen ion concentration. To undo a log base 10, we'll just raise 10 to the power of both sides. 10 to the power negative 5.5 is equal to 3.16 times 10 to the minus 6 molar. This is our hydrogen ion concentration in this slightly acidic solution. The concentration of hydroxide ions can be determined in one of any number of ways. We could take advantage of the fact that Kw is equal to 1 times 10 to the minus 14 power, and Kw is the concentration of H plus cations times the concentration of OH minus anions. We could have also used the derivation pH plus pOH is equal to 14 that we determined just before spring break to accomplish something similar. This means that 1 times 10 to the minus 14 is equal to 3.16 times 10 to the minus 6 concentration of H plus multiplied by the concentration of hydroxide ions. To solve for the concentration of hydroxide ions, we'll divide Kw by concentration of H plus. In so doing, we come up with a concentration of OH minus that is exceedingly small. We get 3.2 times 10 to the minus 9 molar. Like you might expect, for an acidic solution, the concentration of hydroxide ions is far smaller, 3 orders of magnitude and less, than the concentration of H plus cations. H plus cations went out, therefore our solution is acidic. We can take a similar approach to solve the first portion of this next problem, where we're asked to calculate the concentration of H plus of a solution of formic acid whose pOH is 12.12. If we know pOH and what we're after is concentration of H plus, the most logical step towards getting a H plus concentration is first finding the pH. Here we can plug in the pOH that we know is 12.12 and solve for pH. That must be 1.88. From pH, we can calculate the concentration of H plus in this solution. The concentration of H plus must be equal to 10 to the negative 1.88 for the same reason as we described in the previous problem. 10 to the negative 1.88 is 0.0132 molar. Lastly, in this problem, we're asked to calculate the pKa of formic acid. pKa means the negative log base 10 of a Ka value. A Ka value is an equilibrium constant that describes the strength of an acid. and it comes from the equilibrium that our acid establishes. I'm going to get rid of this material for right now, and we'll keep the calculation from the first step in this problem, the concentration of H plus, up above. In order to get a Ka value, we need an ice table. So I've mapped out the steps that we should take to solve this second portion of our second problem. We need to build an ice table for a weak acid, formic acid, find our equilibrium concentrations from the ice table, determine a Ka, and then calculate a pKa. For any weak acid, regardless of which anion brings it to solution, all we really care about is that that weak acid has H plus cations delivered to solution in the first place. Like we discussed before spring break, the generic formula for a weak acid can be given as just HA, with any old anion A bringing H plus to solution, where an equilibrium is established between intact molecular acid, dissociated ions, H plus and A minus. For this reaction, we write a Ka value, which is the concentration of H plus at equilibrium, times the concentration of our anion, in this case formate, but again it really doesn't matter what that anion is, divided by the concentration of intact molecular weak acid. Our ice table for this reaction has initial, change, and equilibrium values. For HA, the initial concentration is given in our problem up above, 1 molar. We know that we started out with 1 molar intact molecular acid. Presumably before that acid dissociates, there's no H plus from it and no A minus from it in solution. As this dissociation tends toward equilibrium, we'll therefore lose some of our molecular acid, gain some H plus cations, and gain a stoichiometrically equivalent amount of A minus. Therefore, at equilibrium, we have 1 minus X for the concentration of HA, X and X for the concentrations of H plus and A minus respectively. Now, before we go any further, let's recognize that we've already determined the concentration of H plus at equilibrium. We know that the concentration of H plus at equilibrium is 0.0132 molar, like we solved for in the first part of this question. In other words, we know the value of X. Anywhere we see X in this ice table, we can plug in 0.0132. Therefore, the equilibrium concentration of HA is 1 minus 0.0132 to 2 digits past a decimal point, that's 0.99. In our Ka expression from up above, we can now plug in equilibrium concentrations of HA, H plus, and A minus. 0.0132 for H plus concentration, and for A minus concentration, 0.99 for HA concentration. Multiplying and dividing, we end up with a Ka value of 1.7 times 10 to the minus 4. Finally, in calculating our pKa, we take the negative log base 10 of that quantity. The negative log of 1.7 times 10 to the minus 4 is equal to 3.75. This is our Ka for this formic acid. In this next section, we're going to talk about how we can use ice tables to deal with weak acid and weak base equilibria. The first thing that we'll discuss here is the concept of percent dissociation. In order to deal with the ice tables in a meaningful way that we're about to work with, we're going to think about the percent dissociation, or alpha, for concentration of H plus cations relative to initial or intact weak acid of molecular form. Alpha, the percent dissociation, for a weak acid is equal to the concentration of H plus at equilibrium divided by the initial concentration of our intact molecular acid multiplied by 100 to give us a percentage. So this alpha is percent dissociation. It tells us what fraction of our weak acid of molecular form HA dissociated, broke up into H plus cations or A minus anions. So now that we've got a new equation, let's use it in a few examples. In example number 1, we're going to think about an equilibrium amount of H plus produced from phenylacetic acid with a concentration of 3.6 times 10 to the minus 4 molar H plus at equilibrium. So our H plus concentration is given, as is our initial concentration of intact weak acid. It doesn't make any difference what phenylacetic acid actually is, so long as we know that it produces just one proton, H plus cation, from its intact molecular formula. Our initial concentration of HA is told to be 1.2 times 10 to the minus 1, or 0.12 molar. The percent dissociation, therefore, alpha, for this acid is 3.6 times 10 to the minus 4 divided by 0.12 multiplied by 100 to give us a percent. Alpha is equal to 0.3%. Effectively, what this result tells us is that this acid, phenylacetic acid, is quite weak. Only 0.3% of molecular phenylacetic acid dissociates by the time equilibrium is established. That's not a whole lot. Compare this to something like hydrochloric acid, where virtually 100% of our molecular formula dissociates. In example 2, we'll up the ante a little bit. Propanoic acid has a pKa of 4.89. We want to know that if we start from a solution of propanoic acid that has an initial concentration of 0.1 molar, what its percent dissociation will be. And then secondly, what its pH is. Let's answer the first part of question number 2 to start, and then we'll think about pH afterwards. Firstly, we know an initial concentration of our intact weak acid, propanoic acid. It doesn't make any difference what its chemical formula actually is, so long as we know that it produces just a single proton by dissociation. We start with 0.1 molar intact weak acid, and we have a means to determine the equilibrium concentration of H plus cations through this pKa value. Well, we just described on the previous slide that if we want to know something about H plus cations, we can write down an equation that shows us equilibrium for any old weak acid. So let's write out what the equilibrium ought to look like for this weak acid, propanoic acid, in question number 2. HA will establish an equilibrium with dissociated H plus cations and A minus anions. This is described by the equilibrium constant Ka for this particular reaction, which is the concentration of H plus at equilibrium times the concentration of A minus over the concentration of HA. And we know that the value of pKa is 4.89. We also know further that pKa is the negative log base 10 of our Ka value. That's equal to 4.89. So Ka must be equal to 10 to the negative 4.89. That works out to be, through calculation here, 1.29 times 10 to the minus 5. About 1.3 times 10 to the minus 5. We have a numerical value for our Ka. What we would like is to figure out the concentration of H plus at equilibrium. For this purpose, we'll need an ice table, just like in our problem on the previous slide. We know an initial concentration of HA, 0.1 molar. From HA, initially, no H plus nor A minus has dissociated. Therefore, we get a change of loss of HA, gain of H plus, gain of A minus. So that we have equilibrium amounts of HA, H plus, and A minus as shown in the ice table here. We'll use this equilibrium concentration of HA in our denominator, X times X in our numerator, and can solve for X with a quadratic equation. We know that Ka, whose value is 1.29 times 10 to the minus 5, is equal to H plus concentration at equilibrium times A minus concentration at equilibrium divided by HA concentration at equilibrium. So, here we can solve the quadratic equation. What we end up with is a quadratic equation that looks like this: 1.29 times 10 to the minus 5 times X minus 1.29 times 10 to the minus 6 is equal to negative X squared. Bring that X squared over to the other side, and we get a quadratic equation that looks like this. We can solve for X by solving the quadratic equation, and we end up with X is equal to 1.1 times 10 to the minus 3 molar. Now, wouldn't it be easy if there were a more convenient way to solve this problem rather than having to slog through the quadratic equation every time we deal with an ice table? Well, there is. We can make a simplifying assumption when we work with weak acid and weak base equilibria. If the percent dissociation for a weak acid or the percent association of a weak base is less than 5%, then we'll assume that so little H plus is established at equilibrium that there's really not much of a significant difference between our initial concentration of HA, that's 0.1 in this example problem, and the concentration of H plus at equilibrium, that's X in this example problem. Like we saw on the previous slide, a change in concentration for phenylacetic acid from example 1 was about 0.01, 0.3% change. That's not a whole lot. The simplifying assumption tells us that our initial concentration of weak acid minus our equilibrium concentration of HA is, for all intents and purposes, insignificant. We can assume that this entire quantity, 0.1 minus X, is small. We'll make the assumption, the simplifying assumption, that 0.1 minus X is so close to 0.1 that it really makes no difference whether we call it 0.1 or 0.1 minus X. In other words, we're going to disregard the X in the ice table for our intact molecular form of our weak acid under this assumption. We can start out making this assumption for every weak acid problem that we work with, and then calculate a percent dissociation at the end to validate it. Under this assumption then, our equation becomes 1.29 times 10 to the minus 5 is equal to X squared over, not 0.1 minus X, but just 0.1. To solve this equation for X is much simpler than the previous. We multiply 0.1 by both sides. To get 1.29 times 10 to the minus 6 is equal to X squared. Now, to solve for X, we can simply take the square root of both sides. And we end up with 1.1 times 10 to the minus 3 molar. For all intents and purposes, the same number that we got by solving the quadratic equation. We'll say that the concentration of H plus at equilibrium for this propanoic acid is 1.1 times 10 to the minus 3 molar. In order to make this assumption, we need to verify it. So we always need to check our assumption by calculating a percent dissociation, alpha. We'll do this after every weak acid problem where we've made a simplifying assumption to avoid solving the quadratic equation. Virtually all the time, it'll work out. Alpha is equal to the concentration of H plus at equilibrium, which we've just now solved for, divided by the initial concentration of HA multiplied by 100. In this problem, the concentration of H plus at equilibrium was 1.1 times 10 to the minus 3 molar, and our initial concentration of HA was 0.1 molar. Here, alpha is equal to 1.1%. And because this value is below a threshold of 5%, we can say that our assumption worked out. We dissociated such a small amount of H plus cations from our intact molecular propanoic acid that there's virtually no difference between the initial concentration HA and the equilibrium concentration of HA. So long as our assumption works out, our percent dissociation, alpha, will be less than 5%. If alpha is 5% or greater, we need to go through the trouble of solving the quadratic equation explicitly. Here, though, it's not, and we've saved ourselves some time in not having to solve a quadratic equation fully. So let's move on with our problem then. If we know that the concentration of H plus at equilibrium under this simplifying assumption is 1.1 times 10 to the minus 3, then the pH of this solution can be calculated from that concentration. The negative log of the concentration of 1.1 times 10 to the minus 3 molar hydrogen cation gives us a final result of 2.96, keeping two significant figures past a decimal point. Here's our pH of our propanoic acid. So here's an example of how to use the assumption to avoid having to solve the quadratic equation. Maybe this is a good point for you to pause and try this problem on your own, and then come back to this video for the solution. So you've all paused, you've all done this problem yourself, and you've got a final answer, but let me walk you through it so that we make sure that we're all on the same page. Benzoic is a weak acid with a Ka given as 6.4 times 10 to the minus 5. It really doesn't matter what formula benzoic acid has, so long as benzoic acid can deliver some H plus cations to solution. We're going to start this problem with a generic weak acid dissociation equation, where we know that Ka is equal to, again, the concentration of H plus at equilibrium times the concentration of A minus all over the concentration of HA. Ka has a value of 6.4 times 10 to the minus 5, so that's equal to whatever the concentrations of all of these things end up as at equilibrium from our ice table. According to our ice table, our initial concentration of HA, our benzoic acid, is 0.9 molar. From it, 0 amount of H plus, 0 amount of A minus initially. We subtract X amount of HA, we add X amount of H plus and A minus. At equilibrium, we assume that we have essentially the same amount of HA as we started with. That X didn't affect HA's concentration significantly enough for it to have changed. Therefore, only H plus and A minus have an unknown concentration at equilibrium. From our equilibrium constant expression, we know Ka is 6.4 times 10 to the minus 5, and that's equal to the equilibrium concentration of H plus, X, of A minus, also X, and of HA, which is effectively 0.9 under this assumption. To solve this problem, we'll multiply both sides by 0.9, and then take the square root of both sides. eventually, we find that x is equal to 7.59 times 10 to the minus 3. Effectively 7.6 times 10 to the minus 3 molar. This is the concentration of H plus at equilibrium. Because we made a simplifying assumption here, let's check that assumption by calculating the percent dissociation alpha given this result for x. Alpha is equal to the concentration of H plus at equilibrium divided by the initial concentration of our intact molecular acid multiplied by 100. In this event, alpha is 7.6 times 10 to the minus 3 divided by 0.9, which gives us 0.84%. Is this a good result or a bad one? Good. It's a good result. You answered correctly, even though I can't hear you right now, because alpha is less than 5%. That means that we don't have to go through the process of solving a quadratic equation. Benzoic acid dissociated so little that the amount of benzoic acid left over at equilibrium is effectively the same as the amount that we started with. So, we can move right along to solving for the pH of our benzoic acid solution. We know the concentration of H plus at equilibrium, and all we have to do to get our pH is plug into our pH equation. The negative log of the concentration of H plus at equilibrium is the pH. So in this case, the pH is 2.12. Good job. I'm sure by this point, all of you are just anxious to learn about what happens if more than one H plus or hydroxide ion can be given up per formula unit of our intact molecular acid or base. And we're going to spend a little bit of time talking about that, but in this course, we're really not going to emphasize it a whole lot. We'll reserve it for future courses like quantitative analysis. First of all, if our acid or base is a strong substance, meaning it's completely soluble or completely dissociates, then our calculation of pH is straightforward. All we have to think about is the stoichiometric equivalent amount of hydroxide ion or H plus cation that's produced from our intact molecular substance. For example, in barium hydroxide, we have a strong base that completely dissociates. It just so happens that barium hydroxide dissociates to produce 2 hydroxide ions for every 1 formula unit of barium hydroxide. This is what the stoichiometry of this reaction looks like. Notice that it doesn't go to equilibrium. Instead, it goes to completion, indicated by a single arrow here in this reaction. To calculate the pH of our solution of barium hydroxide, we'll need to recognize that our major species in solution in barium hydroxide is the hydroxide ion. That dictates pH. We need to calculate first a pOH, and then from a pOH, a pH, knowing that pH plus pOH is equal to 14. To get our concentration of hydroxide ions, all we have to do is take into consideration how much of our intact molecular barium hydroxide we start with and determine a stoichiometrically equivalent amount of hydroxide ions at the end of this dissociation. Because we start with a 0.1 molar solution of barium hydroxide, by the time all of this dissociates, we'll have 0.1 molar barium and 0.2 molar hydroxide ions in solution, just from the stoichiometry of this reaction. That's all we have to do. Our pOH of solution, then, is equal to the negative log base 10 of the concentration of hydroxide ions, so the negative log of 0.2. And our pH will be equal to 14 minus the negative log of 0.2, so plus the log of 0.2. And as this calculates out, we get 13.30. An expected pH for a strong base, something that's very high, close-ish to 14. The difference in working with weak acids or bases, though, is that every single component of our weak acid or weak base is considered when we think about the pH of a weak solution. What we'll think about is a base or an acid associating or dissociating stepwise. For example, phosphoric acid, for whom we can write out a complete chemical formula, H3PO4, has 3 H plus cations that could potentially be given up to solution. For a weak acid or a weak base, we'll think about each H plus or production of OH minus happening stepwise. The very first thing, in other words, that phosphoric acid will do is lose its first proton. This leaves behind the conjugate base H2PO4 minus dihydrogen phosphate. That dihydrogen phosphate can go on to itself lose a proton. It can act like an acid as well as acting like a conjugate base. We say that dihydrogen phosphate is amphiprotic. It loses an H plus cation to generate the conjugate base HPO4 2- hydrogen phosphate, which is also amphiprotic. This thing can move on to produce a final H plus cation and generate the conjugate base of hydrogen phosphate, just phosphate PO4 3-. This stepwise dissociation is associated with an equilibrium constant at each step. There is an equilibrium constant for the loss of the first H plus from H3PO4, which we'll call Ka number 1. There's an equilibrium constant separate and distinct for the loss of a second proton, which we'll call Ka number 2. And for the loss of the final proton, which we'll call Ka number 3. Each of these deprotonation events, Ka1, Ka2, and Ka3, has a measurable equilibrium constant. The first hydrogen that dissociates from phosphoric acid has a Ka value given at 7.2 times 10 to the minus 3. For the second hydrogen that deprotonates, we have a Ka of 6.3 times 10 to the minus 8. For the third H plus that deprotonates, a Ka value of 4.2 times 10 to the minus 13. Notice that these numbers get progressively smaller the more H plus cations is lost by phosphoric acid. That means that it gets more and more difficult for phosphoric acid to lose an H plus cation the more it's already given up. So each one of these substances, H3PO4, H2PO4, and HPO4, is progressively weaker as an acid. And this should have been HPO4 2-. This makes the calculation of pH for phosphoric acid more complicated than the calculations of pHs for other weak acids, and so we are not going to explicitly discuss in this semester how those concentrations of H pluses are calculated, but if you come take my quantitative analysis class, eventually we'll come up with some rules for tackling this sort of problem. What you should be responsible for is recognizing that in an acid or a base with multiple protons to donate or to accept, these donations and acceptances happen in stepwise fashion, where we lose first one hydrogen, then another successively in order. So let's perform one final calculation where we calculate the pH of a base solution rather than an acid solution. We came up with a generic formula for a weak base acting in a solution that looks like this. Any old base that we can call B acts as a proton acceptor when it has a lone pair of electrons somewhere in its Lewis structure. This base reacts with water to abstract a proton from water and leave behind the conjugate acid of our base, BH+. Water, having lost a proton, now exists as only OH-. Bases work to produce hydroxide ions in water. The Kb for this reaction is the concentration of BH+ times the concentration of OH- divided by the concentration of regular old base, B, at equilibrium. We exclude water from this equilibrium expression because we don't include liquids or solids in our K expressions. Other than this reaction, the calculation for pH is more or less the same exact as it was for a weak acid, all the way down to making simplifying assumptions. The only exception here is that at equilibrium, when we use our ice table, we're going to solve for the concentration not of H+, but of OH-. And we'll have one last step at the very end. We'll need to take into consideration that pH plus pOH is equal to 14 to come up with a pH of our ammonia solution, say, in this example. It really doesn't matter if we know what this formula for ammonia is, although we are given it as NH3, and that's something you should know from General Chemistry 1, but every monobasic weak base will proceed with the same generic equilibrium that we've written here. Initially, our concentration of our weak base ammonia is given as 1 molar. We don't care about water because it doesn't show up in our equilibrium constant expression, so we can just ignore that in our ice table. The amount of BH plus and of OH- from ammonia is initially 0. Therefore, we'll lose some amount of our base and gain some amount of conjugate acid and hydroxide ion. We can make a simplifying assumption that at equilibrium, we've lost so little of our intact base to association that we effectively still have 1 molar. That 1 minus X is so close to 1 that it's effectively, for all intents and purposes, still 1. The concentration of conjugate acid and of hydroxide ion at equilibrium are both X. We're given a Kb value for this ammonia, 1.76 times 10 to the minus 5, and told that that's equal to BH plus at equilibrium, X, times OH minus concentration at equilibrium, also X, divided by 1. To solve this, take the square root of both sides, multiplying 1 through, and X ends up being 4.2 times 10 to the minus 3 molar. Keep in mind that because we're working with a base, this is equal to the hydroxide ion concentration at equilibrium. From here, we'll need to recognize that we have to check our assumption before we can move on. But our check proceeds identically to weak acid problems, except here, instead of using the concentration of H plus at equilibrium, we have the concentration of OH minus at equilibrium. Instead of using our intact initial concentration of weak acid, we use our intact initial concentration of weak base. So everything is analogous to our weak acid problems. Our alpha here, which is now percent association, is 4.2 times 10 to the minus 3 divided by 1 times 100, which you can already see is only 0.42%. So, again, is this an acceptable level of association for our base, sufficient to make an assumption that simplifies us having to solve the quadratic equation? Yes, it is. Alpha is less than 5%, so we can go along our merry way and deal with this result rather than having to solve a quadratic equation. All right, so what's the next thing that we can do? The best we can do with the information that we've deduced here is calculate a pOH. We have calculated a concentration of hydroxide ions at equilibrium. the pOH for this solution of ammonia is equal to the negative log of that 4.2 times 10 to the minus 3 molar. Our pOH is 2.38. To get our pH for this solution, which we know ought to be greater than 7, we'll subtract pOH from 14. 14 minus 2.38 is 11.62. A reasonable pH for a base solution. So as a final discussion point on acid and base chemistry, I'd like to talk a little bit about trends in predicting the strengths of acids and bases. For acids in particular, acid strength depends upon two things: the electronegativity of the atom to which hydrogen is bound, and in that same vein, the electron withdrawing power of groups to which an acidic proton is bound. The more electron density that we can take away from a hydrogen atom, the more likely it is going to be to dissociate as a free proton, H+ cation. Electron withdrawing power refers to the electronegativity or electron density around things that bring hydrogen ions to solution. And we say generally, as electron withdrawing power, this thing right here, increases, the acidity, or Ka, of a proton also increases. As we draw more electron density away from a hydrogen, we make it more labile, more likely to be removed from a partner. And in competition with this, we also have the effect of bond strength. The stronger the bond between hydrogen and its partner anion that brings it to solution, the less likely that hydrogen ion is going to be to free up. So as bond strength increases, we expect a decrease in the strength of an acid. So as bond strength between a hydrogen cation and its anion partner goes up, we expect the acidity of an acid, its Ka value, to go down. We can investigate these two competing processes by thinking about how acid strengths rank for acids comprised of similar looking substances. For example, down a group, we can prepare acids of hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid, HF, HCl, HBr, and HI. The electron withdrawing power is strongest for fluorine because it is the most electronegative. However, the bond strength between hydrogen and fluorine is pretty strong. Fluorine is a really small atom, so it's very close to its hydrogen cation partner. In this trend, halogens rank based on bond strength. Bond strength wins out, where in comparing these acids to each other, the weakest bond represents the strongest acid, and the strongest bond represents the weakest acid. So what we say in this trend is that hydrofluoric acid is much less strong than hydrochloric. Hydrobromic is a little bit stronger still than hydrochloric, and of these four acids, we expect hydroiodic to be the strongest. So going down any one group and making acids with successive periods elements, we increase the strength of our acid. We make it more likely that hydrogen can be given up because we decrease the bond strength that hydrogen makes with successive elements down a group. The effect of electron withdrawing power can be seen if we look at acids of similar substances that differ only in, say, the number of atoms of a particular type that are composed in the formula. Say hypochlorous acid versus chlorous acid versus chloric acid versus perchloric acid, HClO versus HClO2 versus HClO3 versus HClO4. In each one of these acids, we add yet one more oxygen atom. We know that oxygen is rather electronegative. The more oxygens we have, the more electron density can be withdrawn from a hydrogen cation that's attached to the ClOx anion. And so the acid that's got the most oxygens, we expect to have the highest electron withdrawing power. We're going to say that HClO4 represents the strongest acid of this bunch because it has the most oxygens in its chemical formula, whereas hypochlorous acid represents the weakest. And these rank in order as they're written. Chlorous acid is stronger than hypochlorous, chloric is stronger than chlorous, and perchloric is much stronger than any of the others. Lastly, we've talked a little bit about amphiprotism as we've discussed water and polyprotic substances like phosphoric acid. In order to determine whether a substance will act like an acid or like a base, if it's amphiprotic, meaning it can act like one or the other, we need to compare their Ka and Kb values. For example, water can act like an acid or like a base. It does both with the same effect because it produces H plus and OH minus anions in the same concentration. But a substance like hydrogen phosphate could act like an acid or a base with differing effect. As an acid, hydrogen phosphate donates a proton. We saw this on a previous slide. HPO4 2- produces a proton to generate its conjugate base, phosphate. The Ka value for this we labeled Ka3 on the previous slide. This has a magnitude of 4.2 times 10 to the minus 13. But we also saw on a previous slide that hydrogen phosphate was the conjugate base of dihydrogen phosphate, suggesting that this substance could just as likely potentially accept a proton as donate it. If hydrogen phosphate accepts a proton, it must accept one from water. And in so doing, it acts like a base to generate dihydrogen phosphate and hydroxide ion. Because it's acting like a base here, this has a Kb value. How do we get a Kb value if we're not explicitly given one? Well, you might recall that just before spring break, we talked about the relationship between Ka and Kb for conjugate acid-base pairs. We said that for conjugate pairs, Ka times Kb is equal to Kw. In this case, we were given Ka earlier on a previous slide for the substance that's the conjugate acid of our weak base hydrogen phosphate. We were told that the Ka for this substance here was 6.3 times 10 to the minus 8. So how does its conjugate base, this thing, react in solution? Well, Ka being equal to 6.3 times 10 to the minus 8 for a conjugate acid, multiplied by Kb is equal to Kw, 1.0 times 10 to the minus 14 at 25 degrees Celsius. Kb for this thing, HPO4 2-, must be equal to 1.0 times 10 to the minus 14 divided by 6.3 times 10 to the minus 8. Kb is 1.6 times 10 to the minus 7. So, how does hydrogen phosphate act when it's in solution? Does it act more like an acid or more like a base? Well, considering that in order to act like an acid, hydrogen phosphate has a Ka of 4.2 times 10 to the minus 13, and in order to act like a base, the same substance has a Kb of 1.6 times 10 to the minus 7. The value that is larger ought to win out. We've got a value for our Kb that's large, a value for Ka that's small. We expect that due to this comparison, Kb wins out. A solution that contains, say, sodium hydrogen phosphate, we expect will be basic. And this is because the Kb for hydrogen phosphate is greater than the Ka for the same substance.